Hey guys, I recently bought a few of these MIT Mini Cheetah Actuators off of AliExpress, and I wanted to make a video showing the internal components as well as the overall design of these actuators. If you're not familiar with it, the MIT Mini Cheetah is a four-legged robot from MIT's Biomimetic Robotics Lab. So this lab works on creating robots which draw inspiration from human and animal biology. So when you want a robot to do things like running or flipping, you need a really powerful and fast-moving actuator. So historically, these actuators have been custom made, and in turn they've been really expensive. So a master's student in the lab named Ben Katz designed an actuator with an integrated controller, and it meets most of these requirements and only costs about $360 to produce. He details the design of the actuators in his thesis, and he published the firmware on a GitHub repo, and a company in China began mass producing these and selling them on AliExpress for $360. Anyway, the purpose of this video is to show the internal components and detail a few of the differences between MIT's actuator and these. So the first thing you're going to want to have is a precision screwdriver set. And you're going to want to grab your 1.5 millimeter hex key bit and unscrew the 6 screws holding on the back cap. So once you've got all 6 screws loose, you can simply lift back up on the cap and it will pop off and expose the driver underneath it. If you look at the back cap, it actually details the connections on the motor. So you have a 5-volt input to power just the driver if you chose to, 24-volt power in for the motor itself, and then you have CAN, and then 2 plugs at the bottom, one of which is for the ST-Link, used to program the STM32 on the driver, and then the other one is a UART port for communicating with it via serial. So you can see these connectors here where you have your ST-Link, then over here is your UART, top left is 5 volts, top right is CAN, and then the center is the actual power for the motor itself. So what we're going to want to do is remove these 3 screws. They're just Phillips head screws that hold the drive onto the actuator itself. So once you've unscrewed the driver board, you're able to lift up on it, and you'll see these 3 phase wires soldered in place on this side. Now, you can't lift the driver board completely off because those phase leads will stay soldered to the board. So what we're going to have to do now is desolder the leads. So the way I'm choosing to do it is to grab each one of these wires with tweezers and pull them out as I desolder the connection from the board. So now we can see the board is loose. That's all the soldering you're going to have to do. So once you've desoldered the board, you can see that it uses the same STM32F series chip as well as the DRV8323 chip by TI. Everything else, like I said, essentially the same. The encoder chip is an MPS Mag Alpha 702. The transceiver is actually an AMS chip instead of an MCP 2562. And then pretty much everything else is the same. Now that we've got our board off, we can actually begin disassembling the actuator itself. So the first thing that we're going to want to do is remove the sealant on the phase wires leading into the stator. So you want to just kind of grab that and move it around a little bit and use your tweezers to kind of just knock some of that sealant loose, just so it doesn't stick as much when pulling off. Then we're going to get our Allen wrench set and unscrew the 8 screws on the frame of the motor. All right, now that we've got our 8 frame screws out, we're going to want to peel back this barcode and remove the 2 screws under it. So as you can see here, there's 2 Torx bit screws. Once you've removed the driver board and these 2 screws, you're going to want to slowly rotate this metal frame and lightly pull on it until you see a gap start to form. You can rock it slightly back and forth, and what you're doing is removing this very tight fit off of this bearing. Once you've removed this piece, you can pull the phase wires out of where they were originally sealed in. Now we're going to want to grab our tweezers and remove the plate that was holding the wires in place. Once you've done that, you now have access to the rotor magnet ring on the outrunner motor that's at the heart of this actuator. Once you've gotten to this point, the next step is going to be to remove the 6 screws holding the gearbox in place on the back half of the actuator. Once all 6 screws are completely loosened, screw 2 of them slightly back in so that it still holds the motor in place when you try and pop the rest of it out. Press lightly around the diameter of the output plate. So we'll just hold the frame and lightly press until we're off of the bearing, at which point we will completely loosen the 2 remaining screws. Once these 2 screws are loose, we can now pop the entire stator and rotor magnet ring off of the frame. So here I have a T motor that's very similar to the one that's used in the MIT actuator. And as you can see, the AliExpress actuator is pretty similar. It uses a similar outrunner motor where a planetary gear set reducer is pressed into the stator. If it makes it easier on us, we can remove the 6 screws by just pressing them out the back half of the actuator. So now that we've removed all 6 screws from the faceplate here, we're going to want to remove the sun gear from the center of the reducer. And the way we're going to do that is by pressing in on this shaft. So this shaft will actually come out the other side along with the rotor magnet ring and leave just the stator and the reducer. So what we're going to do now is take it over to the press and press this out. So I'm back from the press, and as you can see, I was able to push the shaft out of the reducer. So you can see there's the reducer. The sun gear is attached to the rotor magnet ring on the outside, and the stator has the ring gear pressed into it. What we're going to do now is remove the rotor magnet ring from the stator by simply flipping it over and pushing on either side of the stator. Here is the sun gear pressed into the rotor magnet ring, 2 support bearings. So we were able to separate out all of the components. And one thing I didn't mention is this little magnet here. That's actually the magnet that's used for position tracking. So we can take this sheet of magnet paper, and here's a simple cube magnet, and you can see the magnetic field as I rotate the cube magnet from one side to the side where north and south are visible. On the actuator magnet, the direction of magnetism is across the diameter, and the chip on the motor controller picks up on the change in magnetic flux as the motor rotates, and it determines the position based on the direction of this field as it crosses the face of the chip. So moving back to this side, ring gear pressed into the stator, then we've got the retaining ring, and then on the reducer side, we've got a support bearing for the output, as well as 3 dowel pins, and we can go ahead and take these 3 bolts out. So the way we're going to remove these screws is by placing 2 Allen wrenches in the holes on this side and one in between them to act as a lever arm so that we can apply a lot more force to break free each one of these 3 bolts. So now that all 3 are loose, we can come back by and finish unscrewing them. And we can now place our punch into the 3 dowel pin holes and move it around slowly while hitting it lightly with a hammer to begin to pull apart the reducer. And you're going to want to continually rotate this as you're hitting it. And we should see the output plate slowly becoming looser. Once the dowel pins are unpressed, you can see how each gear has a Teflon or brass bushing on top of a 4x8mm needle roller. When comparing the AliExpress motor to the MIT motor, the magnet width on the AliExpress motor is wider. But the most interesting thing is that the component set that the MIT actuator uses is this KHK component set, where we have a sun gear, 3 planet gears, and a ring gear. The sun gear has 20 teeth, the planet gears have 40 teeth, and the ring gear has 100 teeth. Whereas in the AliExpress actuator, the sun gear has 19 teeth, the planet gears have 38 teeth, and the ring gear has 95 teeth. So it's a slightly different number of teeth, but the gear ratio turns out to be the same. Overall, I would say the actuators from AliExpress are basically the same as the MIT actuators. I've also prepared a small demo where you can see I've got a teensy microcontroller communicating to a CAN transceiver that runs straight to the motor. I can then power up the motor to 24 volts. Each CAN message sent to the actuator includes position, velocity, as well as a KP and KD value. So what KP is a desired positional stiffness, so it behaves somewhat like a spring. KD acts as a damper where you can feel some drag proportional to that KD value. So this potentiometer that I have hooked up to the teensy will vary my KP value and in turn change the spring stiffness of the actuator. I can put this lever arm that I 3D printed onto the actuator, and you can see what effect this KP value has. This is a KP value of 4. Now, if I turn the knob and get to a KP value of 6.5, or if I decrease this value all the way to 1.5, you can see how it influences the behavior of the actuator. That's about all I have to show for now. I hope to post a few more videos about the electrical setup and the control code for this actuator in the next few weeks. If you enjoyed the video, please like and subscribe and leave a comment about what other content you might like to see in the future. Thanks for watching.